So we were talking about wave aspects of light. I talked about interference, diffraction, and then polarization of light. There are some more things which I want to talk in this chapter, and today we will be doing three topics. One is scattering of light, other is optical activity, and the third is birefringence. Scattering of light you must be aware of from school days, you know this. In the morning everything is lighted. Even before sunrise you find that okay, everything is lighted and you know that okay, this is the morning. So how everything becomes lighted? Sun rises in east, so light comes from the east only, but you stand in open field, face towards west or north or south or any corner or up, you find everything is lighted. Light is coming to your eyes from all directions. So how is that coming? That is because of scattering. In atmosphere you have molecules, oxygen molecules, nitrogen molecules, carbon dioxide molecules, water vapor and whatnot. And when light falls on these atoms, part of the light scatters in different directions. Atom is a very tiny one. The size would be a fraction of nanometer, whereas light will have a wavelength of a few hundreds of nanometers, 400 nanometer to 700 nanometers, that is the range of visible light. So it's a very tiny particle for light, but still it affects very much, and that is because light is waves and electromagnetic waves. It has electric field which oscillates, which changes with time, and atoms have electrons. So this electric field interacts with the atom, creates a dipole moment if it is not there, and then aligns it, and as electric field itself is oscillating, this dipole moment of atom or molecule also oscillates. An oscillating dipole, like an antenna, it emits radiation, and that is what we call scattered light, and that comes out with its own laws of electrodynamics. If the dipole moment oscillates in z direction, there is a particular pattern of scattered intensity, angular distribution. Mostly things come in the perpendicular plane, so those laws are obeyed and we have light everywhere. And that is also the reason of blue color of sky if you are seeing in the direction opposite to the sun. Because when the light gets scattered by such tiny particles, size much smaller than the wavelength of light, then it's highly wavelength dependent, and the intensity of the scattered light will be in any direction, it will be proportional to 1 by lambda 4. That is called Rayleigh scattering. So shorter wavelengths, the blue end, the violet, blue, green, that end, that scattering will be more, and the red, orange, high wavelength range, that scattering will be small. And therefore when you see in open away on the other direction than the sun, then what you receive is the scattered light, and scattered light will have more of this blue end, and that is why sky appears blue. Okay, so here we have another very interesting experiment. We have water and slight soap dissolved into it, and we have this laser pointer. I will be rotating this laser torch, on its own axis, so that the beam will remain the same, but you focus on how its intensity changes as I rotate the laser. Okay, so now you are seeing the laser beam, and monitor the intensity as I am rotating the torch. I am rotating the torch, and you see what is happening to the intensity. The laser torch is being rotated about its own axis, so the beam remains same, slow. So this is, you see the intensity has gone down. Okay, rotate it further slightly, and intensity is going down further. Yes, stop there and see how low is the intensity. It's the same laser beam, same direction, same water, incident at the same angle of incidence, everything is same. The only thing, I have rotated this cylindrical torch about its own axis. Now the camera is seeing that beam from top. Previously it was from side, now it is from top. And we will again rotate the laser beam, and you look at the intensity. Yes, please rotate. We are rotating, and you see what is happening to intensity. It is going down. Rotate further. Rotate further. It's minimum, very small intensity. Rotate, and now the intensity is again increasing. So as we are rotating the torch, it is again increasing, and now it has become quite bright. Rotate further little bit. Going down, started going down, more, very small intensity now, very small intensity, almost negligible. So that is how. So the intensity of this laser beam in water as seen from top is also changing as I rotate this laser, the torch. Okay, so you have seen the intensity variation. Now why that intensity varies as I rotate this laser torch? Because the beam is going in the same direction. It is entering water in the same direction. It comes out from the same direction. As we had shown earlier, the light that is coming out of this laser pointer or laser torch is largely polarized. That means if the beam is coming out in one direction, the electric field perpendicular to the direction of propagation, but it has a fixed direction, and that direction is fixed with respect to this instrument. So when I rotate this torch about its own axis, everything inside rotates, and therefore the electric field also rotates. So what happens? Let us say the beam is going and electric field is in vertical direction. If the electric field is in vertical direction, the dipole moments will also start oscillating in vertical direction. And if that happens, the radiation from that oscillating dipole will be more in the perpendicular plane, and therefore if I see from the side, I will get more intensity, and if I see from top, I will get less intensity, because a dipole does not radiate much along that direction of the dipole moment, but perpendicular direction, yes, it does with larger intensity. When I rotate the torch, the electric field also rotates, and if the electric field becomes parallel to this horizontal direction, if this electric field becomes horizontal, what will happen? The electric dipole moments will oscillate in this horizontal direction, and therefore if you see from side, the intensity will be much lower. It radiates more in the perpendicular plane, and so if you see from the top, the intensity will be maximum. Now our next topic is optical activity. We have done this scattering, now this optical activity. There are certain kinds of molecules which chemists call chiral molecules. They are not equivalent to their mirror image and so on. So if you have a material having those molecules and send a linearly polarized light through that material, the linearly polarized light remains linearly polarized, but its electric field direction rotates as you go along the length of that material. Now this type of materials are called optically active material because they interact with light and make this change in the direction of the electric field. From the common materials that we use in our daily life, sugar is optically active. So if you have sugar solution and you pass light through this solution, the light is linearly polarized to start with. As it travels in the solution, this direction of electric field or direction of polarization, it will gradually rotate, it will gradually change. So we will see that in this experiment. So here is the apparatus. We have a laser source giving red laser. At the bottom you have this graduated angular scale, and there is a tripod on which we have placed a glass plate, and on that a glass tumbler and this polarizer sheet. This is that glass tumbler and this is the polarizer sheet. On the sheet we have put this pointer, we have fixed this pointer with the sheet so that you can read the position of this sheet on this graduated scale. So at this moment this tumbler is empty, laser is going through this and then through this polarizer and is falling on the roof. So let us look at the spot on the roof. So you can see the spot, and now we will be rotating this polarizer sheet. You can rotate the tumbler only and see when this intensity is minimum. So rotate, it is increasing, increasing, it is increasing, go back, go back, go back, go back, go back. Yeah, now it is decreasing slowly. Go back. Yeah, here it is, here it is. This is minimum, this is almost gone. Now let us see where is this pointer. So read the pointer here, what it reads. The pointer is reading 107. So that is this position. Now we will be putting sugar solution in this glass tumbler. That's it. Very good. Now the laser is going through the sugar solution, then the polarizer, and then on the roof. So let us see the intensity of this spot. So now rotate this polarizer to make this intensity minimum. Yeah, rotate. Yes, it is going down, 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 almost gone. Rotate further, rotate, 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 rotate. Yes, it is again coming back. So go back. Go back, go back, go back, go back, go back. This is the minimum intensity. So let us see what does our pointer say. It was 107 and now it is 121. So the electric field vector has rotated by about 14 degrees when it goes through this length of sugar solution of this particular concentration that we have made. This is optical activity. The rotation depends on the length of the solution and also on the concentration of the solution. So we had done scattering, we had done optical activity, and now we will be doing an experiment based on what we call birefringence. So we have done this and now it is this. You all know when light goes from one transparent medium to another transparent medium, refraction takes place, the speed of light changes. Now for the materials which are optically isotropic, that means all directions in the material are equivalent for light, the speed of light is same whatever way it moves. But there are some materials for which this isotropy is not there and speed of light depends on several other things. One variety is where the speed of light depends on the electric field direction, and that's why it becomes a wave aspect. Our very familiar object, this is cellophane tape, which we use for packing things and closing an envelope and other things, or sticking things together, has this property. Now first let me do an experiment and then we will talk more about it. I have these two polarizers and several glass slides. So on one of the glass slides I will put a layer of this cellophane tape. So I am doing that. So I take a layer and put this layer of tape on this glass slide. Okay. So it's one single layer of tape, you won't be able to see the tape, but perhaps you can see a wrinkle here. So one layer of tape is here. Now if I look through this tape, this glass slide towards some light source, light will get transmitted. I put it between these polarizers. So one polarizer is here, another polarizer parallel to it. So my glass slide is now between two polarizers which are parallel to each other. Perhaps you don't see much of exciting things. And now I am rotating this glass slide and see what happens. The glass slide is at some angle with the edges of this polarizer or these polarizers, and you can see the color appearing in this slide. Rotate it further, the color becomes darker, it's bluish. Rotate it further and now the color is fading away. It almost becomes transparent, no color, and now this is a perpendicular orientation. So remember this color at some angle of 45 degrees or close to that, you have a darkish bluish color. Now let me put one more layer of tape on this and see what happens. I am putting one more layer on that same glass slide. So now I have two layers of tape on this slide. Okay. You may not find much of difference, everything is very transparent apart from the fact that while sticking the tape on glass surface or on another tape surface, there are some wrinkles coming in, but never mind. So put it between the two polarizer sheets in parallel configuration. This is how it looks like. And now let me rotate and see the color and compare with what you had seen with one single layer. Done. Go for one more layer. Let's see what happens if I have 3 layers. I have put one more layer. So now you have 3 layers of this cellophane tape on the glass slide. Bring it between the polarizers, already some color appears. Okay, so start from here and rotate and see the color. This is greenish. With one layer it was bluish, 2 layers it was slightly yellowish, with 3 layers it is close to greenish. Transparent, no color, greenish, again no color. Now there are various other combinations possible. I had put 1 layer, 2 layer, 3 layer. You can do more layers and see. I had put it between parallel polarizers. You put it between perpendicular polarizers and see the colors, they will be different. Now why these colors appear? That is because the tape is a birefringent material. If the electric field is along the length of this tape, the refractive index is different, the speed of light is different, and if the electric field is along the width of the tape, the refractive index is different. Light is going perpendicular to the surface of the tape, so electric field will be in this plane, but then the electric field can be this way or at some angle. So if it is at some angle, if this is the electric field and you take two components, one along this direction and other along this direction, you can call it E1 here, you can call it E2 here. So initially the electric field is this way, then you can think it as a combination of two linearly polarized light, one polarized in this direction, another in this direction, and then the phase difference between these two is 0 and the resultant is again a linearly polarized light. But as it crosses the thickness of the tape, since the refractive indices are different, a phase difference will appear between the two components. The optical path travelled by this component will be n1 times t, and that travelled by this component will be n2 t, and so there will be an optical path difference n1 t minus n2 t, and correspondingly you will have a phase difference which will be 2 pi over lambda n1 minus n2 and t. So depending on lambda, you will have different phase differences, and correspondingly the light which is coming out will have a polarization which could be this way, which could be this way, which could be this way or that way, or could be circular, and so on. So different wavelengths will come out with different kinds of polarization states. And then when I am putting second polarizer to cut one particular component of vibration, so the entire spectral distribution of that light which comes out will be different for different lambdas, and that is the source of different colors appearing.